In Chapter 4, we're going to talk about the key ingredients for inferential statistics. In Chapters 1 and 2, we started to talk about descriptive statistics in terms of what frequency histograms look like and the measures of central tendency like mean, median, and mode, and measures of dispersion like standard deviation. We also kind of peeked at how we can use z-scores as a way to standardize or to show how many standard deviations away from the mean our scores are. We're going to be talking about in Chapter 4 the ingredients that we need to be able to do what's called a z-test in order to determine if our sample is significantly different than our population. We'll get into that in Chapters 5 and 6, but we're going to talk about the ingredients for that. That way we can become familiar with them now before we move on. The normal curve is a distribution that shows us what the spread of the scores is around a particular mean, and it does it graphically. There's also some math to it, but we're going to rely on a normal curve table to help us with that. Let's take a look at a quick demonstration, and I encourage you to follow this link here, www.mathisfun.com, etc., in order to run this out a little bit longer, because we're only going to look at it for just a few moments to get the idea of it. So let's go ahead and look at that demonstration. What we're going to observe is a series of dots or balls or whatever you want to call them that will fall down this grid that looks a lot like Plinko from The Price is Right. And what you're going to recognize is that as each disc goes down, it hits a peg and it goes either left or right. That's called a binomial decision. It will go left or right and then hit another peg and go left and right, etc., etc., etc. Now, the likelihood that the disk makes as many left choices as right choices is 50-50. So if we had to guess each time which channel that disk would fall into, we'd say right in the middle. It would take 1, 2, 3, 4, 5, 6 consecutive right decisions. That'd be like flipping a coin 6 times in a row and having it come up all heads. It would have to make 6 consecutive similar decisions to fall into the channel all the way to the right and symmetrically to the left. So as you can see, the probability of getting a disk that falls into the right channel or the left channel is a lot less than if it falls into the middle channel. And then the probability gets smaller as you get away from the mean. So the likelihood that you have a disk that falls into channel 6 is a lot less than channel 5 and 4 and 3. The likelihood that you get a disk that falls in channel 2 is the same as channel 4. Let's go ahead and start this, and we'll speed it up so that we can actually see some results. So we're going to speed it up to 200 so it'll keep going. And as you can see, we're not getting many disks that fall to the far regions. We got one so far. As you can see, we start to have some disks that fill up more toward the middle and very few toward the ends. Eventually, once we had a theoretical infinite amount of observations, we would have a shape that approximates a normal curve. And as you can see, it's starting to get there, but as we get more cases, we're going to get a better approximation of the normal curve itself. Usually, it takes, maybe up to 1,000 cases for it to start smoothing out. We're not going to watch this demonstration for very much longer. You can go ahead and go to that website that is linked in the PowerPoint presentation, and you can run this yourself just to see what it looks like after so long. But as you can see, it is a relatively symmetrical distribution. We have about 320 cases, and we have 6 and 5, so that's pretty close. 29 and 23, not too bad. 91 and 84, not so bad, and then 107 right in the middle. And as you can see, it starts to approximate the normal curve. So with that comes the idea that we can discern the probability of a particular response on a histogram, for example, based on what we know about normal curves in general. We'll get to that in a moment. We need to review the central limit theorem. The central limit theorem is when we have a mean or a center of a distribution that the other scores tend to gravitate around. The central limit theorem also states that the more cases that are present, the more likely we are to see a normal curve. The central limit theorem is based on the mean of a distribution. The mean of the distribution is in the middle, and the other scores are centered around it. When we think of an example, we can think of something like reaction time. So imagine you're asked to press the button when a light turns red, just a simple reaction time test. When you press the button, it might have a mean, you might have 3/4 of a second or 75 hundredths of a second response time. You might have a 1 second response time. You might have a 40-second response time. But let's say that on average, you have a response time of 0.75 seconds with a standard deviation of 0.125 seconds. Okay, let's just start with that. That means that on average, you press the button 3/4 of a second. And on average, you're about 1/8 of a second off from that. Let's take a look at some examples of histograms and how they can be represented by that same idea. If we had 10 people in our study of reaction times, you can see that their scores are kind of all over the place. And really what that means is that there are so few people in the study that we don't start to see a normal curve develop. As you can see, it tries to approximate the normal curve based on the data, but look at this. We have, let's see, 4 people that scored somewhere in the 6/10 of a second range. Then we have 8/10 to 1 second, and then we have one person above 1 second. So as you can see, with only 10 people in the study, when we take a look at their response times, we get some kind of mean, a standard deviation, but it's really far off. So, for example, the mean of this distribution, you can barely see it there, but is 0.8 seconds with a standard deviation of 0.15 seconds. If we had 30 people in our sample, so if we ask 30 people to do their reaction time study, you can see that the normal curve starts to look like something, where we have some smaller amounts on the extremes and then more toward the middle. In this particular example, there are 30 people in the study. We have a mean of 0.73 seconds and a standard deviation equal to 0.118. With 100 people in the study, we start to definitely see the shape of the normal curve. Even without the superimposed shape on top of it, we start to see that we have a distribution that tends to center around a particular mean. In this case, the mean is 0.74. Then in the last example, with 1,000 people, you definitely see the normal curve. So with 1,000 random people, and you take their response times, and you plotted them in a histogram, you will start to see a very definite normal curve develop. What's interesting about the normal curve is that we can also determine what percentage of people fall in a particular range. Now let's take our z-scale, for example. We talked about z-scores and the z-scale in chapter 2. If we had a mean of whatever it is, it would have a z-score of 0 because the mean of all z-scales is 0. So if you had a z-score of 0, then you have the mean of whatever you're measuring. We could call it reaction time, that's fine. And then if you had a z-score of +1, you'd be 1 standard deviation above the mean, and then 2, and then -1, -2, etc. We can generally break down, I'm missing a percent there. We can generally break down where our percentages fall on the normal curve. For example, we know from math that if a z-score is between 0 and +1, then that means that it includes 34% of the scores on the normal curve. Said another way, 34% of the scores are between a z-score of 0 and +1. 14% of the scores are between a z-score of 1 and +2, and 2% of all the scores are above a z-score of 2. Because it's a symmetrical distribution, 34% of the scores in a distribution are between 0 and -1, 14% are between -1 and -2, and 2% of all the scores are below -2 z-scores. Now just kind of thinking about that, you could see that if somebody had a z-score, or if they had a score that was more than 2 standard deviations above the mean, that means that they are scoring like 2% of the entire distribution. That's kind of interesting to know. We're going to rely on this kind of logic going forward. Now, when we use z-scores and raw scores on the normal curve, you can see that it makes a little bit more sense than just saying what the z-score is. Let's go back to our IQ example. So an IQ of 100 has a z-score of 0 because the mean of all IQ scales is 100 with a standard deviation of 16. That's from chapter 2. So if you had an IQ of 100, that means you have a z-score of 0. If you had an IQ of 68, that means you have a z-score of -2. You can fill in the blanks from the rest of the data. Now, if I ask you a question like what percentage of the scores are between an IQ of 68 and 84, you could look at the IQ scale and say, well, 68 is -2 z-score, 84 is a -1 z-score. That means that the number of scores between 68 and 84 is 14%. Or said another way, 14% of the scores are between a z-score of -2 and -1. Or an IQ of 68 and 84. It's the same thing. Next question, what percentage of the scores are between an IQ of 100 and 68? Well, 100 is at the mean, 68 is -2. I can look at what my breakdown is, so I can say that 34 plus 14, or 48% of the scores, are between an IQ of 68 and 100. Last, what percentage of the scores are between an IQ of 84 and 132? Well, 84 and 132, I can add those together and I can say 34 plus 34 is 68 plus 14 is 82. So that means that 82% of the scores are between an IQ of 84 and 132. Now what if I asked you a question like, what percentage of the scores are below an IQ of 84? Well, I would find 84, and if I said below, that means I'd be going negative. So the number of scores below an IQ of 84 is 14 plus 2. That's 16%. So 60% of the scores are below an IQ of 84. What about below an IQ of 132? Okay, I can look at where my 132 is, and I can figure this out 3 ways. I can say, well, 132 is here. All the scores below it are 14 plus 34 plus 34 plus 14 plus 2. That equals 98. I could do it that way. Or I could insert a little bit of logic and say, well, I know that 50% of the scores are below the mean because the mean is where the middle of the group of scores is. So 50% of the scores are below the mean, and 50% plus 34 plus 14 equals 98. One last way you can do it is by using deduction, and you can say, well, all the scores below 132 are all of the scores except for 2%, because 2% is above 132. So you could just say that 100% minus 2% is 98%. So there are 3 ways to go about doing that. And what percent of the scores are below an IQ of 100? Well, we know that the mean of the IQ scale is 100, so that means that 50% of the scores are below it. That's kind of the nature of the central limit theorem. If I asked you what percentage of the scores are above an IQ of 100, well, you could use the same logic and say, well, 50% are above an IQ of 100. What percentage are above 116? Well, that is everything above 1 standard deviation positive, so that's 14 plus 2 equals 16. And the same kind of logic for above a 132. The number of percentage of scores above 132 is 2%. There are some terms that we need to become familiar with when we talk about the normal curve. One of those is tail, and you're going to get familiar with the idea of percentage in tail. Percentage in tail. That is the distance or the probability between the score and the tail. When we talk about the tail, we're talking about all scores that are above or below a certain point. So in this example, there are 2 tails, and in every curve there are 2 tails. We may not always be interested in both tails, but there are 2 tails. So if I were to ask you, what is the percentage above the z-score of whatever this is, looks like maybe positive 1.75, you would say, well, there are this many scores in the tail. So the tail is everything above a certain point if it's positive, or below a certain point if it's negative. Okay. The other bit of information that we have to get familiar with is what's called the score to the mean, or what we call percentage of the mean to the z. And that means we take the score to the mean. So whatever the x or z score is, that distance from that score to the mean. That is called the score to the mean. We will use both of those pieces of information when we are trying to figure out probability. Now, when we're talking about percentages, it's interesting to understand that when we talk about the percentage of scores, we're also talking about probability because it's a likelihood. Something happens a percentage of the time, there's also a probability. The percentage and the probability are the same numbers, except for percentages are multiplied by 100. So if a probability is 0.5, you multiply that by 100 and that becomes 50%. Those are the same things. So now that we have some curve terminology under our belts, let's take a look at the normal curve table to help us understand how we're going to use that terminology. So the normal curve table is a way for us to circumvent the long, awful equation that we would use in order to determine the probability that a particular score occurs on the normal curve. We would be really close to math if we use that long equation. The good news is that we use a normal curve table like most other people out there. Before we jump into the normal curve table, let's get familiar with some of the things that we need to know. The normal curve table tells us a few things. It tells us the distance from the mean to the score. Okay, so it tells us this. It will tell us the distance from the mean to the score, or whatever the score is to the mean. It's the same thing. It also tells us the distance from the score to the tail. It'll tell us how far it is from this score to the end of the distribution, which is theoretically infinite, by the way, but it'll tell us what percentage of scores are below a certain score in the tail or above a certain score in the tail. It'll also tell us the distance based on the direction of the hypothesis. We're going to get into that a little bit more when we talk about hypothesis testing in chapters 5 and 6, but we do need to be aware of what a one-tailed and two-tailed test are now. That way we can just use that information later as opposed to learning it all in the same chapter. We do all of this with z-scores, by the way. We don't use raw scores because we know that raw scores can be different for every scale. For example, there is not a normal curve table for age, or for weight or height, or for numbers of cheeseburgers you ate in a week. There just aren't tables for that. So what we do is we convert all of our raw scores to z-scores, and there is one z table. That's one of the conveniences of standardizing. Now, when we have some kind of information about a score, like a z-score is equal to -2, so whatever your score is, it is 2 standard deviations below the mean, we can do it in our heads using just our conventional cutoffs. And what we have to rely on are these percentages, the 2, 14, 34, 34, 14, and 2. We can apply those to this first example. So if I asked you what the mean to z equals for this particular example, or what the probability is of getting a score between a -2 and the mean, you could say, well, I know that the first breakdown is 34% and the second one is 14. If I add those together, it's 48%. So you could say that 48% of the scores are between a z-score of -2 and the mean of 0, the mean z-score of 0. Now, if I asked you what percentage of the scores are between a z-score of -1.7 and the mean, you might get a little caught up in that because it's not just a matter of using our percentages. The good news is that we can use the normal curve table, which will tell us the percentage of scores between a z-score of -1.7 and the mean. So let's consult our z-table. By the way, your z-table is in the appendix of your book. You can find that by looking at the glossary. It's different for each edition, so I can't give you a page number, but they are back there. So if I asked you what percentage of scores are between a z-score of -1.7 and the mean, you can consult the normal curve table by doing a little bit of searching, but it's not too bad. So let's take a look at this, and I've taken a snippet from the page that has the answer on it. So if I look at the top of my z-table, I recognize that there are a couple of graphical representations. The first one is the mean to the z. See, it's a shaded area that shows some random z-score and what the mean of the distribution is. And that's what that means, is that it's going to tell you what the percentage is between the score that you're looking at and the mean. The other graphic is from the z to the tail. Now, Please also recognize that there are two columns in this, column 1 and column 2. Don't read all the way across because those aren't the same pieces of information. So here's what we do. We find the z-score that we're interested in. This is negative 1.7, and oh, wait a second, those are all positive. That's okay. It's a symmetrical distribution, so the numbers will be the same. The distance between a z-score of negative 1.7 in the mean is the same as a z-score between a positive 1.7 in the mean because of symmetry. So I go down and I find my z-score of 1.7, and then I go over to the column that I'm interested in, which is percentage of the mean to the z, and the answer is 45.54. So what the answer is there are 45.54% of the scores between a z-score of negative 1.7 and the mean. Something that you'll notice also is that the percentages don't exactly align to our conventional breakdowns. So if we use this conventional breakdown, you'll recognize that it goes to 2 standard deviations. The normal curve table goes out many standard deviations, so that means that these percentages get redistributed to many standard deviations, usually 3 or more. So what that means is that instead of being nice numbers of 2, 14, 34, 34, 14, and 2, if you add another standard deviation, you have to borrow percentages from each of these columns to fill in the last one. The good news is that the difference is pretty small and we don't have to worry so much about it. So remember our example, we were looking at the percentage of mean to z. The answer is 45.54% of the scores are between a z-score of negative 1.7 and the mean. More practically, we like to look at the percentages of scores from, the percentages of scores from a particular z-score to the tail. So if I ask you a question like, what is the percentage of scores between a z-score of 1.21 and the tail, you could look at that also in the z table. In the z table, we would find the z-score that we're interested in this case is 1.21, so I scroll down to 1.21, and I look over not at the column that says percentage of mean to z, but the percentage in the tail. So I find that if I have a z-score of positive 1.21, then the percentages of scores in the tail is 11.31. Another way to say that is 11.31% of the scores are above a z-score of 1.21. So let's go ahead and try some examples. And for these examples, it looks like we're going to need the z formula because we want to convert these raw IQ scores to z scores. So let's go ahead and just replicate the z formula. Z equals x minus m minus standard deviation. And because we're working with IQ scores, let's go ahead and bring forward the information we know about IQ scores. So for IQ scores, the mean is equal to 100. The standard deviation is equal to 16. So let's go ahead and bring down our question. The question is, what percentage of z-scores are above an IQ of 84? Well, let's convert that to a z-score real quick. That way we can plug it in on our normal curve, and then we can start to answer the question. So if we plug this information in, z is equal to 84 minus 100 divided by 16, which is negative 16 divided by 16, which is equal to negative 1. So we want to know what percentage of the scores are above a z-score of negative 1. Well, we know already that the percentage of scores that are above the mean is equal to 50%. So it's going to be some amount plus 50%. So let's go ahead and consult our normal curve table and find the percentage from the mean to the score. So the z-score is negative 1. We want to find the percentage of scores between a z-score of negative 1 and the mean. So let's go ahead and bring over our z-table real quick. So our z-table, I've got it highlighted here, but what we find is our z-score of negative 1, and remember it's symmetrical, so it can be positive 1, that's fine, it's the same thing. And we go to our column that says percentage of mean to z, and the answer is 34.13. So what we know is that 34.13% of the scores are between a z-score of -1 and the mean, plus 50% of the scores above the mean, which means that 81.43% of the scores are above an IQ of 84. Or another way of saying that is 81.43%. Oh, I'm sorry, I transposed that in my head. Again, you're screaming at me and I'm not even listening. Let's try that again. That should be 34.13. And that makes this 84.13. I'm glad I have you guys to let me know of things like this. There we go. Whew, that's better. So the percentage of scores above a z-score of -1, which is the same as above an IQ of 84, is 84.13. Let's try another example. What percentage of scores are below an IQ of 123? Well, let's go ahead and start with our z formula again and convert that IQ to a z-score. That way we can plug it in and compare it with our normal curve table. So an IQ of 123, lost my marker, an IQ of 123 minus 100 divided by 16 is equal to 23 divided by 16, which is equal to 1.44, and I rounded a little bit. So a z-score of 1.44, right about there, positive 1.44. We want to know the number of scores, the percent of scores below that figure. And remember, we already know that 50% of the scores are below the mean, so really what we need to find is this distance here. So we can bring over our normal curve table again, and we can find the z-score of 1.44, which is kind of next door, and we want to find the percentage from the mean to the score. So we want to find percentage of mean to the score for a z-score of 1.44, and the answer is 42.51. So 42.51% of the scores are between a z-score of positive 1.44 and the mean. I'm going to move this down just so it doesn't look as confusing. That was 42.51 plus 50%, which gives us 92.51%. So 92.51% of all the scores are below an IQ of 123. Next example. What is the percentage of scores between an IQ of 64 and 100? So we can use, again, a little bit of logic and find that 100 is the mean. We know that 100 is the mean of our IQ scores, right? So what that means is we want to know something about this mean, and we want to know the number of, or percentage of scores between an IQ of 64 and 100. So we want to know some score to the mean, but we need to find what that z-score is for an IQ of 64. So let's go ahead and plug it into our formula. 64 minus 100 divided by 16 is equal to negative 36 divided by 16, which is equal to negative 2.25. So negative 2.25 is somewhere in this neighborhood. So we want to find the number of scores between a z-score of 0, because we know that the mean has a z-score of 0, and negative 2.25. So really what we want to do is use our normal curve table to find the percentage of scores between the score and the mean, and the score we're using is negative 2.25. So let's go ahead and bring our normal curve table back and find 2.25, and it is all the way down here. 2.25, and we are looking at the column that says percentage of mean to z, and the answer is 48.78. So 48.78% of the scores are between a z-score of negative 2.25 and the mean. Okay. Last two examples, probably a little bit faster because we're not going to have to consult the z-table for it. So let's go ahead and take this all out. Okay, so we want to know the percentage of scores above a z-score of negative 32, and a z-score of negative 0.32, not 32, negative 0.32 is somewhere in this neighborhood. Get my pen back. So the number of, or percentage of scores above a z-score of negative 0.32. Okay, we know that this amount is 50%. So we need to find what the distance is between negative 0.32 and the mean. So we're going to go back to our normal curve table. Let me put this in here real quick before I do it. 50% plus whatever this amount is. And our normal curve table, we will look at 0.32, which is way up here. 0.32 is right here, and we are looking at percentage of the mean to the z, and that gives us a score of 12.55. Which equals 62.55%. Now, you'll notice that even though it's a very small amount, that's 12% of the whole curve, but look at how much taller this curve is in between these 2 points, as opposed to, say, this point and this point here, where I'm just kind of wiggling my cursor here. This has a lot less space than this does. So you can see that as you get farther away, there is, it's actually logarithmic, but there is a change in the amount of percentages at a given physical distance on the curve. And the last example, percentage of scores below a z-score of 2.21. So let me go ahead and delete this. I missed some. Okay, so we're looking at all the z-scores below 2.21. So 2.21 is kind of in this neighborhood. Z is equal to 2.21. And we're looking for the scores that are below that. So let's go ahead and do our assumption again. Our assumption is that 50% of the scores will be below the mean. We just need to add that to the distance from the mean to a z-score of 2.21, and we're in good shape. So let's go back to our normal curve table one last time and find 2.21, which is right here, and we are concerned with the percentage of the mean to the z, which is the second column, and our answer is 48.64. 48.64. Add those together, we get 98.64% of the scores are below a z-score of 2.21. This is good exercise and practice in order to get you going in the right direction for making decisions about significance, beginning in chapters 5 and 6. So do pay attention to this and what it means that we are using z-scores as a way to measure percentages or probabilities. Because remember, probabilities and percentages are the same thing. The probability of getting a 98.64% is 0.9864. You just divide it by 100. So it's the same thing. We'll talk more about that when we get to chapters 5 and 6. Let's wrap up by using some terminology that you're going to be familiar with between the work that you're going to be doing in the book and for your final project in this class. But we're talking about sample versus population. We need to use these terms very carefully, and I'm going to have to undo a little bit of confusion that the book might give you. So let's pay attention real closely to the distinction here, especially when it comes down to talking about symbols that we will use for sample and population. So a population is a complete group of interest. It doesn't have to be everybody in the world. It just has to be everybody who you are interested in. And that's actually easier than it sounds. A population could be all Americans. By the way, it'd be very difficult to actually get information from all Americans, but that would be considered a population, every single individual American. Students in this class is a population because we are concerned about only those people. If everybody who is in a class is in attendance that day, you have the entire population of students in that particular class. Left-handed humans is a population. That would be everybody who is left-handed. Again, it'd be hard to actually access everybody who is left-handed to ask them a question, but that would still be considered a population. Individuals in a control group in an experiment would be a population. You could have individuals who are in an experiment, they've gone through the control group. That's the population of control group participants. Now, by the way, that would still be a sample of individuals in the entire universe, but if you were just interested in individuals who are in that control group in that experiment, you could use the population as that parameter. The amount of corn stalks in a 100-acre field is a population. And when you think about that, you're like, well, that is a lot of corn stalks. It sure is. And if I asked you a question like, is the corn good? You would say, well, I don't know, because I haven't tried all the stalks and all the ears on all the stalks of corn in the 100-acre field. Okay, that would be a silly response, right? Because we know that it's not always reasonable to access the population to answer questions. We usually access a sample in order to answer the questions. So if we looked over a 100-acre field that had a bazillion stalks of corn in it, and I said, hey, is the corn good in that field? You could say, well, I'll try some and see. What you're really saying is, I will sample the population to determine if the corn is good. And what's interesting is that as long as that ear of corn that you sample is like the rest of them, you can make an assumption about the rest of the ears of corn. However, let's say that you grabbed an ear of corn that had bugs in it, and you ate it, and you're like, oh, this doesn't taste good. This corn is no good. And you made that assumption about the rest of the population, you would be incorrect. That's a very subtle example, but it really leads to a piece of core logic for later on in the course. So understand that the sample must be like the population in order to make assumptions. And even if it is, by the way, we'll make mistakes, and we'll talk about that later on in the course. So if we look at the 5 groups above, which of those groups do you think it would be reasonable to study as a sample, as opposed to the entire population? So let's take a look at this. All Americans. Can we get access to all Americans? Not really. Would it be more reasonable to study a sample of those individuals? Yes. What about students in a particular class? Can you have access to all students in a particular class? Sure. So that means that you could study the population and do just fine. What about left-handed humans? Not so much. You can't get a hold of them all. You can't study them all, so you're more likely to sample left-handed humans than you are to use the population. The individuals in a control group, again, we have access to that group, the entire group, so we could use that whole group as a population. The amount of corn stalks in a 100-acre field. Even though you have access to all the corn in the field, you aren't going to take all of them to see if they taste good. You're going to sample some of them to see if they taste good. Kind of like the example from the book where they talk about soup, about sampling soup and determining if the soup is any good. Okay? It's important to understand that we can sample a group as long as the sample looks like the rest of the group. We can make some assumptions about it, knowing that we're probably going to make an error altogether when we make an assumption. So when we are talking about sampling versus population, we want to know about the members of the group. Okay? Our sample needs to look like the population. And in some cases, we're just trusting that our sample looks like the population because we can make mistakes when we sample people. Let's say that we are sampling people at Olivet College and we want to know how they like seminar. Okay, and let's say that we sampled 100 people on campus, but let's say that 30 of them are part of the professional programs, and they don't have department seminar, and we ask them about it. Well, our sample wouldn't look like the population, so the results that we got wouldn't really reflect the true population. We would need to make sure that everybody in the sample actually had department seminar and then ask them about it. Some of the things that affect the trustworthiness or the validity of our sample is the number of cases. That means how many people are we sampling, and the quality of the cases, meaning do the qualities of the cases match the qualities that we would expect from the population. Now, here's an example of what I mean by the number of cases. Let's say that we wanted to sample all the student athletes at Olivet College. And let's say that there are 400 student athletes at Olivet College, and we sampled 10 of them. Does that sound like a representative sample? Yeah, I mean, maybe if they're all athletes, they're actually athletes, and that's good, but there aren't a lot of cases there that start to approximate the diversity of the student athletes in terms of what sports they play and everything. What if we had 390 of them? Well, geez, that's pretty trustworthy because really we're just missing a few of them. As you can see, the closer you get to the population, the more trustworthy your results are. What that also means is the closer you get to the actual population, the less mistakes you're going to make. Because if you ask 390 student athletes a series of questions and you assumed that the rest of the population would respond like them, you'd probably be okay, because really you're just talking about, would 10 other people behave like 390 people who come from the same population? They probably would. But if you only sampled 10 people and you said, well, these 10 people are going to speak for the other 390, boy, you'd probably be making a lot of mistakes because you don't have enough data to really safely make that conclusion. So when we talk about the mistakes that we make by not having a good sample, we're talking about error. Sometimes it's called sampling error. In statistics, we build in error. We assume that we're going to make a mistake, which is why what we try to do is we try to make a decision on whether or not our results are trustworthy with about a 5% level of error that we will take into consideration. Again, we'll get more into that in chapters 5 and 6, but for now it's good to have this basic understanding. Here's the example from the book. It's just a fun little diagram, and it's interesting to see. Let's say that you looked at a population of soup. So it's all the soup you made. It's a pot of soup, it's the population. And you wanted to see if it needed more salt. If you took a spoonful of it and tasted it, and it tasted bland, and you added salt to it, you'd probably be okay. But let's say that you had put some salt in earlier, and you forgot to stir the pot. And you went in to check and see if that salt that you added earlier made a difference in the overall taste. And let's say that you happened to scoop out much of the salt that you put in because you forgot to stir it. And you tasted it, and it tasted really salty. You'd say, oh, geez, this soup is really salty. It doesn't need any more salt. You would be making a mistake because you sampled a particular part of the population that was not representative of the rest of it. It's a fun example to help drive it home a little more concrete. Something that you'll want to think about, especially when you're looking at your final projects, are the idea of the accessible population. If you are doing a study where you are sampling somebody from Olivet College, and by the way, if listening to this and you are not in research methods also, this doesn't apply to you, the fact that you'll have to think about who you're sampling because you'll be given something. It just kind of dawns on me that other people are watching this right now who probably aren't having to do the same kind of final project that you would if you were in this class with research methods. Okay, enough about that. The population is the blue disk, and it includes the target population and the sample. The overall population is are the individuals that have characteristics that you're interested in studying. The target population are people that you have access to within reason. And the sample are the people who you actually solicit to engage in your study. Using an example at Olivet College, let's say that you wanted to just sample everybody at Olivet College. So you sampled Olivet College, and the population is everybody at Olivet College. The target population are people who have email addresses, let's say. So the target population is everybody at Olivet College who has an Olivet College email address. And for the sake of argument, let's say that not everybody at Olivet College has an email address. Maybe a new student got enrolled and doesn't have an email address yet or something. Or maybe they're a dual enrolled student and they're using their personal email address or something like that, okay, for the sake of the example. So the target population of all the Olivet College students would be only those with email addresses. The sample would be those who responded and are participating in your study. So the target population are the people who you asked to be in the study. The sample are the final group of people who are actually in your study. Now, the book uses population 1 and population 2, or the population from the sample and the population from the population, kind of those kind of broad terms. I want you to understand that when we are talking about the population of individuals, that is the larger group from that our sample comes from, we're going to be using the symbols that are in Greek. So the Greek letter mu, and I'm going to draw that so that you can kind of see it. The Greek letter mu is the mean. So the mean of the population is equal to the Greek letter mu. The standard deviation of the population is equal to lowercase sigma. Looks like an O with a hat on it, I guess. I don't know. And then the variance of the population is equal to sigma squared. We'll be using those symbols in lectures and things, even though in the book it talks about population mean and sample mean using the words. I want to use the symbols because I think the book oversimplified that in this version. Another reason why is because you will see these Greek symbols in research, and I want you to be familiar with those. The book does a really good job of using concepts and using things written out whenever they can. In this particular edition, the Statistics for Behavior and Social Sciences, a brief course, is a different, it's based on the same book, but it's a different approach to it, and it kind of oversimplifies this aspect. So we're going to be using mu for population mean, lowercase sigma for standard deviation of the population, and lowercase sigma squared for variance of the population. The mean of the sample, standard deviation, and variance of the sample will use the same type of symbols that we've had before. But we are going to be using these, so please commit these to memory and understand that there's a difference there. All right, so that wraps up Chapter 4, where we talk about the normal curve, sample versus population, and probability. I look forward to seeing what you're able to retain from this so that we can go forward in chapters 5 and 6 and really apply this stuff to examples. If you have any questions, feel free to reach out.